In this video, we'll be talking about Chapter 15, Section F, on scalar multiplication. Now, we've been talking about vectors, and remember that vectors have both magnitude and direction. But a scalar is a quantity that has magnitude only. So, a scalar is a vector without direction. And really, scalars are just ordinary numbers. So, 2, -1, these are scalars because they have no direction associated with them. Now I can multiply vectors by scalars. For example, if I have vector A, I can multiply vector A by 2. And essentially, if I have vector A here, what that does is it doubles the length of vector A. I can also multiply vector A by -1. And so -1 is a scalar, and essentially what that does is it gives me the negative of the vector. It reverses the direction, and it has the same magnitude. In this example problem, I'm going to show you two different ways that we can simplify vector expressions using scalars. I'm going to show you the graphical way, or the geometrical way, and then I'll show you the algebraic way to solve or to simplify these expressions right here. So we're given vector R has an x component of 3 and a y component of 2, and vector S has an x component of 2 and a y component of -2. And we're asked to find first this expression right here, 2r plus s. So what I can do geometrically is graph vector R, and because I'm multiplying it by a scalar of 2, I'm just gonna graph it twice. Okay, so I can start here, and I can go to the right 3 spaces, and then up 2. So that's my first R vector. Then I can go to the right 3 spaces, and up 2 again. And so now I have 2r. And then I can do my s vector, which is going to the right 2 and down 2. And so this is my s vector. And then my resultant vector would be this guy right here. Remember, starting at the start and ending at the end of the progression of vectors. And then it's just a matter of counting on the graph the x and y components. So I have 1, 2, 3, 4, 5, 6, 7, 8 units in the positive x direction, and I have 1, 2 in the vertical direction. Okay, I can do something very similar for vector r minus s, and I'll do that in green here. Again, I can start with vector r, go over 3, up 2. And then minus s is really -1 times s. So I will go -2 and then up 2. Okay, and my resultant here is going to be actually over 1 to the right and then up 4. So that's the graphical or geometrical way of simplifying these vector expressions. Now I'm going to show you the algebraic way. And to do that, we need to know that if k is a scalar, and we have a vector in component form, we'll use a and b for our components, then this is equal to this vector in component form. The x component is k times a, and the y component is k times b. So now I can use this to solve these expressions algebraically. The first one is 2 times vector r plus vector s. Well, this is, you can sort of think about distributing this 2 into the vector. And so really I have 6, 4 as my first vector, 2, negative 2. And remember, to add those, I simply add the x components together and then add the y components together. And that's going to equal 8, 2, which is exactly what we got from the graph. And I could do a similar exercise. I'll switch to green here for the second example. And we have vector r, which is 3, 2, minus vector s, and this is really minus 1 times vector s, which is 2, negative 2. I'm going to change this to an addition problem. And we have this. So our resultant vector is 1, 4. And again, that's what we received from the graph.